Complex numbers, or numbers involving, conceptually you can think about it as the square root of -1, I, are essential to understanding quantum mechanics, since some of the most fundamental concepts in quantum mechanics, for instance the wave function, are expressed in terms of complex numbers. Complex analysis is also one of the most beautiful subjects in all of mathematics, but unfortunately in this course I don't have the time to go into the details. Lucky you, perhaps. Here's what I think you absolutely need to know to understand quantum mechanics from the perspective of complex analysis. First of all, there's the basic definition. I squared is equal to -1, which you can think of also as I equals the square root of -1. In general, a complex number, z, then, can be written as the sum of a purely real part, x, and a purely imaginary part, I times y. Note, in this expression, z is complex, x and y are real, where I times y is purely imaginary. The terms purely real or purely imaginary, in the context of this expression like this, x plus iy, something is purely real if y is 0, something is purely imaginary if x is 0. As far as some notation for extracting the real and imaginary parts, typically mathematicians will use this funny calligraphic font to indicate the real part of x plus iy or the imaginary part of x plus iy, and that just pulls out x and y. Note that both of these are real numbers. When you pull out the imaginary part, you get x and y. You don't get iy, for instance. Another one of the most beautiful results in mathematics is e to the I pi plus 1 equals 0. This formula kind of astonished me when I first encountered it, but it is a logical extension of this more general formula that e raised to a purely imaginary power iy is equal to the cosine of y plus I times the sine of y. This can be shown in a variety of ways, in particular involving the Taylor series. If you know the Taylor series for the exponential, the Taylor series for cosine of y, and the Taylor series for sine of y, you can show quite readily that the Taylor series for complex exponential is the Taylor series of cosine plus the Taylor series of sine. And while that might not necessarily constitute a rigorous proof, it's really quite fun if you get the chance to go through it. At any rate, the trigonometric functions here, cosine and sine, should be suggestive, and there is a geometric interpretation of complex numbers that we'll come back to in a minute. But for now, know that while we have rectangular forms like this, x plus iy, where x and y, the nomenclature there is chosen on purpose, you can also express this in terms of r e to the I theta, where you have now a radius and an angle. The angle here, by the way, is going to be the arctangent of y over x. And we'll see why that is in a moment when we talk about the geometric interpretation. But given these rectangular and polar forms of complex numbers, what do the basic operations look like? How do we manipulate these things? Well, addition and subtraction in rectangular form is straightforward. If we have two complex numbers, a plus ib plus, and we want to add to that a second complex number, c plus id, we just add the real parts, a and c, and we add the imaginary parts, b and d. This is just like adding in any other sort of algebraic expression. Multiplication is a little bit more complicated. You have to distribute, and you distribute in the usual sort of draw a smiley face kind of way. A times c and b times d are going to end up together in the real part. And the reason for that is, well, a times c, a and c both being real numbers, a times c will be real. Whereas ib times id, both being purely complex numbers, you'll end up with b times d times I squared, and I squared is minus 1. So you just end up with minus bd, which is what we see here. Otherwise, the complex part is perhaps a little more easy to understand. You have I times b times c, and you have a times I times d, both of which end up with plus signs in the complex part. Division, in this case, is like rationalizing the denominator, except instead of involving radicals, you have complex numbers. If I have some number a plus ib divided by c plus id, I can simplify this by both multiplying and dividing by c minus id. Note the sign change in the denominator here. C plus id is then prompting me to multiply by c minus id over c minus id. Now, when you do the distribution there, for instance, let's just do it in the denominator, c plus id times c minus id, my top eyebrows here of the smiley face, c squared times id, or c squared plus, now, id times minus id, which is, well, I'll just write it out, I times minus id, which is going to be d squared times I times minus I. So I squared times minus 1. And I squared is minus 1. So I have minus 1 times minus 1, which is just 1, so I can ignore that. I've just got d squared. So what I end up with in the denominator is just c squared plus d squared. What I end up with in the numerator, well, that's the same sort of multiplication thing that we just discussed. So the simplified form of this has no complex part in the denominator, which helps keep things a little simple and a little easier to interpret. Now, in polar form, addition and subtraction, well, they're complicated. Under most circumstances, if you have two complex numbers given in polar form, it's easiest just to convert to rectangular form and add them together there. Multiplication and division, though, in polar form have very nice expressions. q e to the I theta times r e to the I phi. Well, these are just all real numbers multiplying together, and then I can use the rules regarding multiplication of exponentials, meaning if I have two things like e to the I theta and e to the I phi, I can just add the exponents together. It's like taking x squared times x to the fourth and getting x to the sixth. But qr e to the I theta plus phi. So that was easy. We didn't have to do any distribution at all. The key fact here is that you add the angles together. In the case of division, it's also quite easy. You simply divide the radii, q over r, and instead of adding, you subtract the angles. So polar complex numbers expressed in polar form are much easier to manipulate in multiplication and division, while complex numbers represented in rectangular form are much easier to manipulate for addition and subtraction. Taking the magnitude of a complex number, usually we'll write that as something like z, if z is a complex number, just using the same notation for absolute value of a real number, usually is expressed in terms of the complex conjugate. Now, the complex conjugate, notationally speaking, is usually written by whatever complex number you have, here in this case x plus iy, with a star after it. And what that signifies is you flip the sign on the complex part, on the imaginary part. X plus iy becomes x minus iy. The squared magnitude then, which is always going to be a real and positive number, this absolute value squared notation, is what you get from multiplying a number by its complex conjugate. And that's what we saw earlier with c plus id. Say I take the complex conjugate of c plus id and multiply it by c plus id. Well, the complex conjugate of c plus id is c minus id times c plus id. And doing the distribution, like we did when we calculated the denominator, when we were simplifying the division of complex numbers in rectangular form, just gave us c squared plus d squared. This should be suggestive if you have something like x plus iy, that's really messy, x plus iy, and I want to know the squared absolute magnitude. Thinking about this as a position in Cartesian space should make this formula, c squared plus d squared, in this case, just make a little more sense. You can also, of course, write that in terms of real and imaginary parts. But let's do an example. If w is 3 plus 4i, and z is minus 1 plus 2i, first of all, let's find w plus z. Well, w plus z is 3 plus 4i plus minus 1 plus 2i. That's straightforward. If you can keep track of your terms, 3 minus 1 is going to be our real part, so that's 2. And 4i plus 2i, which is plus 6i, is going to be our complex part. Sorry, our imaginary part. Now, w times z, 3 plus 4i times minus 1 plus 2i. For this, we have to distribute. like usual. So from our top eyebrow terms here, we've got 3 times minus 1, which is minus 3, and 4i times 2i, both positive. So I have 4 times 2, which is 8, and I times I, which is minus 1, minus 8. Then, for my imaginary part, I guess the mouth and the chin, if you want to think about it that way, I have 4i times minus 1, minus 4 with the I out front, will just be minus 4 inside the parentheses here. And 3 times 2i is going to give me 6i plus 6 inside. The end result you get here is 8, or minus 8 minus 3 is minus 11, and minus 4 plus 6 is going to be 2. So I get minus 11 plus 2i for my multiplication here. I guess if I'm going to circle that answer, I should circle this answer as well. Now, slightly more complicatedly, w over z. W is 3 plus 4i, and z is minus 1 plus 2i. And you know when you want to simplify an expression like this, you multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. So minus 1 minus 2i divided by minus 1 minus 2i. And if we continue the same sort of distribution, we'll do the numerator first. Same sort of multiplication we just did here, only the signs will be flipped a little bit. We'll end up with minus 3 plus 8 instead of minus 3 minus 8. And for the imaginary part, we'll end up with minus 4 minus 6 instead of minus 4 plus 6. And you can work out the details of that distribution on your own if you want. The denominator is not terribly complicated, since we know we're taking the absolute magnitude of a complex number by multiplying a complex number by its complex conjugate. We can just write this out as the square of the real part, 1, plus the square of the imaginary part, minus 2, which squared is 4. So if I continue this final step, this is going to be 5. This is going to be minus 10i, and our denominator here is just going to be 5. So in the end, what I'll end up with is going to be 1 minus 2i. So it actually ended up being pretty simple in this case. Now for the absolute magnitude of w, 3 plus 4i, you can think of this as w times w star square root. You can think of this as the square root of the real part of w plus the imaginary part of w. Sorry, square root of the squared of the real part plus the square of the imaginary part, which is perhaps a little easier to work with in this case, so you don't have to distribute out complex numbers in that way. Real part is 3, imaginary part is 4, so we end up with the square root of 3 squared plus 4 squared, which is 5. Now this was all in rectangular form. Let me move this stuff out of the way a little bit. And let's do it again, at least a subset of it, in polar form. In polar form, w, 3 plus 4i, we know the magnitude of w, that's 5. So that's going to be our radius, 5. And our e to the I theta, where theta is, like I said, the arctan. Since complex numbers are so important to quantum mechanics, let's do a few more examples. In this case, I'm going to demonstrate how to manipulate complex numbers in a more general way, not so much just doing examples with numbers. First example, simplify this expression. You have 2 complex numbers multiplied in the numerator, and then a division. First of all, the first thing to simplify is this multiplication. You have x plus iy times ic. This is pretty easy. It's a simple sort of distribution. We're going to have x times ic, that's going to be a complex part. So I'm going to write that down a little bit to the right, ixc. And then we're going to have iy times ic, which is going to be minus yc. That's going to be real. We also have a real part in the numerator from the d here. So I'm going to write this as d minus yc plus ic. That's the result of multiplying this out. That's then going to be divided by f plus ig. Now, in order to simplify this, we have a complex number in the denominator. You know you need to multiply by the complex conjugate and divide by the complex conjugate. So f minus ig divided by f minus ig. Now, expanding this out is a little bit messier, but fundamentally you've seen this sort of thing before. You have real part, and imaginary part in the numerator. And then you're going to have imaginary part, and real part, imaginary part. And what you're going to end up with from this first term, you get f times d minus yc. From the second term, you have minus ig times ixc, which is going to give you xcg. We have a minus I times an I, which is going to give us a plus. Incidentally, if you're having trouble figuring out something like minus I times I, think about it in the geometric interpretation. This is I in the complex plane. This is minus I in the complex plane. So I have one angle going up, one angle going down. If I'm multiplying them together, I'm adding the angles together. So I essentially go up and back down, and I just end up with 1 equals I times minus I. Otherwise, you can keep track of I squareds equals minus 1s and just count up your minus signs. This, then, is the real part. Suppose I should write that in green, lest my fonts get too confusing. Excuse me. So that's the real part. The imaginary part, then, is what you get from these terms here. I'm going to write an I out front, and now we have xc times f, so xcf with an I from here. And then we have d minus yc times ig, which I'll just write as g d minus yc. In the denominator, we're now multiplying a number by its complex conjugate. You know what to do there. F squared plus g squared. This is just the magnitude of this complex number. Sorry, squared magnitude. Now, this doesn't necessarily look more simple than what we started with, but this is effectively fully simplified. You could further distribute this and distribute this, but it's not really going to help you very much. The thing to notice about this is that the denominator is purely real. We've also separated out the real part of the numerator and the imaginary part of the numerator. Yeesh. My handwriting is getting messier as I go. Imaginary part of the numerator. So we can look at this numerator now and say, this is the complex number, real part, imaginary part, and then it's just divided by this real number, which effectively is just a scaling. It's a relatively simple thing to do, to divide by a real number. As a second example, consider solving this equation for x. Now, this is the same expression that we had in the last problem, only now we're solving it for it equal to 0. So from the last page, I'm going to borrow that first simplification step we did, distributing this through. We had d minus yc for the real part, plus ixc for the imaginary part, and that was divided by f plus ig. If we're setting this equal to 0, the nice part about dealing with complex expressions like this is that 0, treated as a complex number, is 0 plus 0i. It has a real part and an imaginary part as well. It's just kind of trivial. And in order for this complex number to be equal to 0, the real part must be 0 and the imaginary part must be 0. So we can think of this as d minus yc plus ixc. This has to equal 0 and this has to equal 0 separately. So we effectively have two equations here, not just one, which is nice. We have d minus yc equals 0 and xc equals 0, which, unless c equals 0, just means x equals 0. That's the only way that this equation can hold, is if x equals 0. The key fact here is to keep in mind that in order for two complex numbers to be equal, both the real parts and the imaginary parts have to be equal. As a slightly more involved example, consider finding the cubed roots of 1. Now, you know 1 cubed is 1. That's a good place to start. We'll see that fall out of the algebra pretty quickly. What we're trying to do is solve the equation z cubed equals 1, which you can think of as x plus I y, where x and y are real numbers, cubed, equals 1. Now if we expand out this cubic, you get x cubed plus 3x squared times iy plus 3x times iy squared plus iy cubed. And this is going to have to equal 1. Excuse me. Equal 1. Now, looking at these expressions, here we have an iy, here we have an iy squared. This is going to give me an I squared, which is going to be a minus sign. And here I have an iy cubed. This is going to give me an I cubed, which is going to be minus I. So I have two complex parts and two real parts. So I'm going to rewrite that. X cubed, and then now a minus sign from the I squared, 3xy squared, plus, pulling an I out front, the imaginary part then is going to come from this 3x squared y and this y cubed. So I've got a 3x squared y here, and then a minus y cubed, minus coming from the I squared. And this is also going to have to equal 1. Now, in order for this complex number to equal this complex number, both the real parts and the imaginary parts have to be equal. So let's write those two separate equations. X cubed minus 3xy squared equals the real part of, this is the real part of the left-hand side, has to equal the real part of the right-hand side, 1. And the imaginary part of the left-hand side, 3x squared y minus y cubed, has to equal the imaginary part of the right-hand side, 0. So those are our two equations. This one in particular is pretty easy to work with. We can simplify this. This is, we can factor a y out. This is y times 3x squared minus y squared equals 0. One possible solution then is going to come from this. You know, you have a product like this is equal 0. Either this is equal to 0 or this is equal to 0. And saying y equals to 0 is rather straightforward. So let's say y equals 0. And let's substitute that into this expression. That's going to give us x cubed equals 1, which might look a lot like the equation we started with, z cubed equals 1, but it's subtly different because z is a general complex number, whereas our assumption in starting the problem this way is that x is a purely real number. So a purely real number, which when cubed gives you 1, that means x equals 1. So x equals 1, y equals 0, that's one of our solutions. Z equals 1 plus 0i, or just z equals 1. Now, we could have told me that right off the bat, z cubed equals 1. Well, one possible solution is that z equals 1, since 1 cubed is 1. The other thing we can do here is we can say 3x squared minus y squared is equal to 0. This means that, I'll just cheat a little bit and simplify this, 3x squared equals y squared. Now I can substitute this in, this y squared, into this expression as well. And what you end up with is x cubed minus 3x, and then y squared was equal to 3x squared. So 3x squared is going to go in there. That has to equal 1. Now let's move up here. What does that leave us with? That says x cubed minus 9x cubed equals 1. So minus 8x cubed equals 1. This means x, again, being a purely real number, is equal to minus 1/2. minus 1/2 times minus 1/2 times minus 1/2 times 8 times minus 1 is equal to 1. You can check that pretty easily. Now, where does that leave us? Where did I go? That leaves us substituting this back into this expression, which tells us that 3x squared equals y squared. X equals minus 1/2, so 3 minus 1/2 squared equals y squared, which tells you that y equals plus or minus the square root of 3/4 if you finish your solution. So now we have two solutions for y here coming from one value for x, and that gives us our other two solutions to this cubic. We have a cubic equation. We would expect there to be three solutions, especially when we're working with complex numbers like this. And this is our other solution. Z equals minus 1/2 plus or minus the square root of 3/4 I. So those are our three solutions. Now, finding the cubed roots of 1 to be these complex numbers is not necessarily particularly instructive. However, there's a nice geometric interpretation. The cubed roots of unity like this, the nth roots of unity, doesn't have to be a cubed root. All lie on a circle of radius 1 in the complex plane. And if you check the complex magnitude of this number and the complex magnitude of this number, you will find that it is indeed unity. To check your understanding of this, a slightly simpler problem is to find the square roots of I. Put another way, you've got z, some generic complex number here, equals to x squared x plus iy. Quantity squared, if that's going to equal y, we'll expand this out, solve for x and y in the two equations that will result from setting real and imaginary parts equal to each other. And same as with the cubed roots of 1, the square roots of I will also fall on a circle of radius 1 in the complex plane. So those are a few examples of how complex numbers can actually be manipulated. In particular, finding the roots of unity, there are better formulas for that than the approach that we took here.